Hello, Science Nines. I'm Mr. Hardy. I know some of you maybe have met me or knew me already, but I haven't had a chance. I won't have a chance to actually interact with you guys, so I'll miss out on that. But anyway, I'm gonna go. I make videos like this for a number of the notes that we have, and so I'm gonna start with the notes I've already sent, and we'll go from there. So, a lot of the first part to electricity is learning the vocabulary, and so the first thing I want to emphasize is this drawing right here. What we need to know about all materials, and you guys have already learned this in chemistry, is that they're made up of atoms. And an atom has electrons, neutrons, and protons. The electrons, of course, are negatively charged, okay? And they basically whiz around what's called the nucleus of an atom. I know that's not on here, but I think you guys have heard that term before. The nucleus is where the neutrons, which are neutral, they don't have a charge, and the protons reside. Okay. Now, when we're talking about electricity, we're really going to talk about the movement of the electrons. See, these electrons, they're kind of out here and they're whizzing around, and they have occasion to jump to the next atom. Okay. And they can just keep doing that. They can move from atom to atom uh, under the right conditions. And the movement of those electrons is what we know as electricity, or we'll talk about two types of electricity. The first type is static electricity. And you get static electricity, the easiest way to get it is if you take two materials and you rub them together. Okay, like your socks on the trampoline, or like a balloon, where you rub it on your hair. You'll get electrons that will jump from basically the balloon or from your hair to the balloon, basically, or vice versa, depending on the materials. Okay. So, um, what's really cool is in a thundercloud, what you have is you have water droplets that are in the water that are in the cloud, and they bump and crash into each other. A lot of times they are high enough in altitude that they freeze, and so they turn into ice. And all that bumping and crashing results in static electricity. And for the sake of lightning, in fact, maybe I could just sketch that here quick. For lightning, what happens is in a thundercloud that's high up in the sky, okay, and then you got the earth down below, the uh, the water droplets that are lighter, they tend to be charged positively. Oops, sorry. They tend to be charged positively, and they are near the top, whereas the electrons are negative, or the parts of the cloud that are negative are at the bottom. And so the cloud gets huge, it gets a really strong negative charge. What happens is the Earth is normally neutral. So the Earth has equal numbers of protons and electrons below. And if you get a strong negative charge in the cloud, then these electrons actually go deep into the earth. So they get moved down here. And so what happens is the surface of the earth right underneath a thundercloud starts to become positive. It's actually really nerving if you're ever near a thundercloud, um, because you might start to become positively charged. So your hair will stand up on the back of your neck, and that's a dangerous sign because it means you're starting to get positively charged. So anyway, objects on the earth, like we could say you, are they can become positively charged as well. And so what happens is the um, electrons actually form what are called step leaders, and they actually this is maybe I need to make this a little bit bigger, but they form what are called step leaders that actually here, let's just make more space here altogether, um, that come down from the cloud, because the cloud, because it's negatively charged, these step leaders will start to migrate towards the positive charge that's waiting on the ground. And so they kind of branch and fork and split, but it isn't lightning yet because it hasn't made connection to the ground. As the step leader gets closer to the ground, whatever's on the ground, because it's positively charged, it will start to release. I'll maybe change colors here, but they'll start to release positive streamers. These are called streamers that come up from the ground. Okay, they're they're weakly luminous, so it means they're a little bit they do generate light, but they're hard to see, and they'd only exist for a few milliseconds. But anyway, once those connect, then the electrons that are all in the cloud, at least in the bottom of the cloud, they now have a pathway to take to the ground, and they'll take it, and that's a lightning strike. So it's a huge amount of charge. The same thing happens, but at a really small scale when you know when you rub your hand on your bed sheets at night. Like if you turn off all the lights and then rub your hand on the bed sheet, you'll see little blue sparks flying off. That's static electricity. Obviously, at a huge scale, lightning is a great example of static electricity. So that's what the first one is. Okay. Now, these others here, I think we've already discussed them. The proton has the positive charge, the electron has the negative charge. What we need to know about charges, and we've already discussed it, is that they can either attract each other or they can repel. And so opposite charges attract and like charges repel. That's actually down here, number 9. So you need to know that. I know it's a really simple concept, but there's a lot of complex applications for it. So as long as you remember that, I think you'll see those no problem. So um, what we do say is number 5 is if you have equal numbers of charge, positive and negative, then you're neutral. And if you've built up more electrons than you have protons, we call that a negative charge. Okay. Now I want to draw your attention to this little picture over here, because um, if you bring a charged object close to a neutral one, there's a couple of things that can happen. In materials called insulators, which I think you've heard of, insulators resist the flow of electricity. They tend to be things like rubber and glass and wood. And if you brought a negatively charged object here, these little these little objects here are all negative. Okay, so if we had something that we had rubbed, like a piece of rubber or a balloon or something, and we brought it near this green object, which could also be a balloon, say, but it's neutral. What happens in an insulator is something we call a charge shift in insulators. And so what that means, and that's what this is showing right now, in insulators, they hang on to their electrons really tightly, and so the electrons aren't free to move and jump to the next atom. And so in this picture, it shows that all the electrons have basically shifted over to the right side of their protons or of their nuclei, but they haven't left. Okay, they haven't abandoned their protons, okay, or abandoned their nucleus. They've just kind of shifted over. Now, this is enough, though, that for a neutral object, collectively, this side of the balloon is positive, and collectively this side is negative. Okay, it kind of makes a little bit of a shift, so that the side on the left is partially or slightly positive, and the other side slightly negative. That's enough to cause attraction. Okay, so even though it's neutral, this balloon will actually be attracted to that charged, well, this is, I don't know what that is. Looks like a charged lightning rod or something. Okay, so that's a charge shift. Now, we can just sketch it here, but in a conductor, that's what this next one says. You actually get something called a charge migration. Now, if you think of a migration, that's a great distance. I always think of the Arctic tern. It's a migratory bird. It migrates from the South Pole all the way to the North Pole. It's like the farthest migration of any animal on the planet. Okay, so a migration is a big movement. So if this green object was a conductor, let's say it was a metal sphere or something like that, then these electrons would not do a shift. What they would do is they would migrate. They would all pile up all the way out here. So all those negatives would actually migrate. This one would go over here, that one, this one come way over. They would just be repelled by all of these guys, okay? And so now the attraction would be really positive. On the left-hand side, this side would be really positive and that side would be super negative, okay? So there would definitely be attraction in a conductor, even though, again, collectively, the charge is neutral. Now, as soon as they touch, well, you're going to have a charge transfer. Like some of these electrons will jump onto there, and it'll become negative. The green sphere would also become negative. Okay, so that's the difference between a charge shift and a charge migration. As you know, when you get an electric shock, we have a name for that actually. We call it an electrical discharge. Okay, so that's a term you should know. Now, in the video, if you've watched them, this device here was highlighted. Okay. Oh, whoops. It's called a Van de Graaff generator. It was made by a professor at MIT in the United States. That's the Massachusetts Institute of Technology. And it's a very clever device. It's super fun to play with because you can generate all kinds of static electricity. Now, but that's static electricity. And yes, it's generated, as I noted in number 10, by friction. There's actually a rubber belt that contacts a metal brush, and that contact generates static electricity, which charges the dome. Okay, if you saw that in the video. Now, static electricity is horrible, though, for operating electrical devices, as it notes there in number 1 for current, because that energy just gets discharged all at once, and then it has to build up again and then be discharged again. So it's not very reliable. What we really want is what we call current, and that is the constant flow of electrons. So a steady flow of electrons, that's awesome. We can use that for all kinds of things. So in general, you need at least 2 conditions. There's several others, but you need at least 2 if you want electricity to flow continuously. And that is, you need a continuous pathway. So you need what's called a circuit, and we're going to learn about those shortly. But you also need a source. So you also need some electricity to come from something. Now, we have some electrical terms that we're going to start learning, and you guys might already know these, but the rate at which electrical current flows, we measure that rate in amps. Amps are actually a measure of charge per second. And electrical charge is measured in a unit called coulombs. A coulomb is just a huge, huge number of electrons. You don't need to know this, but it's actually 6.25 times 10 to the 18th electrons. Okay. It's a huge, huge number. It's, that's a billion electrons. 1 coulomb of charge is almost, I think of it as a lightning strike. Like there's a huge number of electrons that get released all at once. Most of the things that you encounter in your day-to-day life that are electrostatically charged have nowhere near that many of electrons. Okay, not even close. Like it's really, really small amounts. But anyway, Charles Coulomb was a French scientist who was studying actually the force between charged objects. And so the unit of charge got named after him. Okay. Actually, amps is really from another French scientist named Ampere was his name. And so we have a lot to thank the French for in terms of our understanding of electricity. But we always use the English version, which is just amp, which is shortened. But if you see Ampere, that's also a measure of current. Okay. But again, it's 1 coulomb of charge per second. And if you saw the video on, I'd encourage you to watch the video on current and voltage, because it's really, really good. Okay. So materials that easily move charge through them, or that let charge go through them, are called conductors. And a circuit is that path that lets electricity flow. So I want to draw a little bit on this picture here, because this is a simple circuit. We're going to learn to draw these a bit later. A circuit has our source. We can see we have a cell here, has a positive and a negative terminal. We've got a wire hooked up to a load. Now, I know a load, it says later, it's a device that converts electrical energy into something else. A light is a great example of a load. Okay, it takes electrical energy and converts it into light and heat. So I'm actually going to change to show electrons. Now, electrons always flow from the negative terminal to the positive terminal. And so I'm going to actually show that. Actually, let me get this just a little bit bigger. We're going to show these as a coulomb of charge is really a whole bunch, or it's really like a bundle or a unit of electrons. So we're going to show these electrons kind of flowing through the circuit and making their way back to the positive terminal. So this, what I'm illustrating here is the flow of electricity. It goes from the negative terminal to the positive, okay? And as electrons come out, they have a lot of energy. In fact, in this illustration here, I'm going to show that by kind of wrapping these electrons in red here, and the thickness of the thickness of how much I'm illustrating them with is proportional to how much energy they have, okay? So initially they have lots of energy as they come out of the negative terminal. Then when they get to the light, what happens here is some of that energy is, actually most of it, if it's working well, will be released as light and heat. Okay, so I'm showing that in red as well because it's still energy, but it's a different kind. And then after the electrons have gone through the light bulb, I won't show too many of these, but they basically don't have any more energy. So as they will continue to move because there is current, but they will arrive at the positive terminal with essentially no energy. Now, energy is measured in joules. So, and you may have heard that term already. Sorry if I can use my lovely pen here. It's starting to wear out on me. Joules. So that's Joules. Okay. And we could say that at the negative terminal, that every single coulomb of charge has 9 joules. Okay. So we could say there's 9 joules per coulomb. If I'm going to say these blue dots are coulombs, okay, so we're going to say that it's just a whole bunch of electrons, right? We learned that number already. And those coulombs of charge are moving through the circuit. But by the time we get to the positive terminal, we'll say that it's basically lost all of its energy, okay? It now has 0 joules per coulomb by the time it gets to the positive terminal. So this electrical energy, we call it electrical, or the energy it carries, sorry, we call that electrical energy, okay, as it moves around. And voltage, this is the other term you've probably heard of. Voltage is a measure of how much electrical energy each charged particle carries. We have different terms for that, though. We also call it potential difference, or just the word potential. The units, of course, are volts, but we can use a device called a voltmeter and actually measure the voltage in a circuit. So I might just change this here. So if we get a voltmeter, okay, there's lots of different kinds of voltmeters. Often they have like a little dial here, and then they have a digital screen, and then they have 2 probes. So what we'll do is we'll take one probe and we could touch it right there. We could take another probe and touch it right there. Okay. And when we would do this, it would read the potential difference in energy from this position to that one. And as you can see, I did this on purpose. Initially, we had 9 joules per coulomb of energy, and then over here we had 0 joules. So the voltage here would be 9 joules per coulomb, or 9 volts. So what you need to know is that a volt, 1 volt, and I guess I could add that up here, 1 volt is equal to 1 joule per coulomb of charge. Okay. I know, and joules, again, I know joules is another term that you maybe haven't heard of. It's a measure of energy. That's also named after another scientist named James Prescott Joule, who did some research on understanding energy. Okay. So, two terms. You need to know current at this point. Current is measured in amps, and it's 1 coulomb of charge that passes a point in a wire per second. Okay. Current's the easier one. It's just like thinking of like the flow of electrons. Voltage is the trickier one, but it's not too bad if you can see the examples. 1 volt is equal to 1 joule of energy per coulomb. Okay. So just a couple of quick safety things you need to know as well. If you, yeah, that's the example says, if you were to contact a high voltage power line with, an electrical device, or if you had a ladder or an auger is a classic one. If any of you deal with farm machinery, that's really dangerous because it basically creates an unintended pathway for the electricity that's flowing in the high voltage power lines. So we call that a short circuit. There's lots of ways to create that, but typically they're bad. Typically a short circuit sends electricity where it isn't supposed to go. Okay. But as with any circuit, you need a complete pathway, otherwise the electricity can't flow. So we talked about insulators, which electricity does not flow well through. We're talking about plug-in devices here. That's just an extra bit of information. You typically are on any electrical device, you should be able to find a voltage rating and a current rating, so that most devices are already designed to just plug in the wall. You don't even think about it. But they've been tested and designed to take just the right amount of current and voltage. Another safety feature, though, is the third prong in a 3-prong plug, which is shown right here. Okay, that bottom plug actually doesn't connect with electrical power or electrical energy that's in your house. It's a safety device that safely can transfer any extra electrical energy or current that's maybe going somewhere it's not supposed to, and it connects to a separate line that goes into the ground, and it is called the electrical ground wire. Okay, and so you'll notice some plugins only have 2 prongs. They don't have the ground wire prong, and so they don't have this added safety feature. Okay, but that's exactly what that is. Fuses and circuit breakers are another one. They're kind of fun. Fuses are actually a fuse. Most of the time, it's actually just kind of a cylinder like this, and inside the cylinder is a coil of wire, and that hooks up to the circuit like this, and then the circuit goes away. That coil of wire is designed to heat up if too much current is flowing. So too much current starts flowing for some reason, this little wire here, it heats up and then it breaks. Okay, just burns right through. So if it breaks, then the circuit is no longer complete, and then everything shuts off. So sometimes we say, "Oh, you blew a fuse." There's lots of different shapes for fuses. You can see them in vehicles and in other electrical devices. A circuit breaker doesn't. It does break the circuit, but it doesn't burn a coil. Circuit breakers are what are in your basement, in your space. Sometimes they call it a fuse box or a circuit breaker box. But it has a whole bunch of circuit breakers that if too much current starts to flow through a certain circuit, it actually heats up. There's some cool processes that happen, but the short of it is that the circuit breaker opens. So it'll trip and it'll open up, and then everything that's on that circuit doesn't work anymore. And so when that happens, often you go downstairs and you look at it, you're like, which circuit breaker has tripped, and then you move a lever over and back and reset it. And that's again another safety device for controlling current in your house. Number 7, I did just note that I should have put that up with lightning, but lightning tends to seek the highest point on the horizon to discharge. So the last part of this introductory notes is on cells and batteries. And we're all familiar with cells and batteries. We use them all the time. The term, though, is an electrochemical cell, because what happens is we're getting electricity from a chemical reaction between typically two different metals, and you'll see that really easily when we get into wet cells. But in general, there are two types of cells. There's a dry cell and a wet cell. And what's different is what's called the electrolyte. Okay, now that's down here in number 4. The electrolyte is basically it's the medium through which the chemical reaction can happen. And most of the time it's a liquid, but in a dry cell, as noted in number 2, it's in a paste. Okay. And so if you grab, like a double A battery, we call it, right? And you shake it, you can't hear anything. There's no liquid like sloshing around inside it, okay? Because it's a paste. It's kind of like a heavy toothpaste or something. And you can see it here in this dry cell. The electrolyte is kind of the red, kind of looks like a sponge material that will allow the chemical reaction to happen. So what we have though here is we have a negative electrode, which is kind of this surface cylinder out here, and then you have a positive electrode, which is up in here, more embedded inside. And so I know it's kind of basically it's a couple of different cylinders, and there's some really cool structures that are in place to let this all happen. You should know though that the electrons that are on the negative electrode, they will travel through the electrolyte. Basically, this is called a collecting rod on the inside. And then the electrons will move through the wire. As we already saw, they'll lose some of their energy, they transfer their energy to the light bulb and so on, but then they'll make their way up into the positive terminal. And in what are known as primary cells, okay, I'm kind of jumping around a little bit here. These primary cells, in a primary cell, you cannot recharge it. What happens is all those electrons, they wind up here in the positive terminal, and they're happy just to stay there, okay? So once all of the electrons have drained all their energy and they've all made it to the positive terminal, then the battery or the cell is no good, and we chuck it. Now, if it's a secondary cell, then it can be reversed. What we do is we basically run electricity into the actual cell, and we make the electrons go back. Okay, we tell them to go back to where you came from, to the negative terminal, and then it can go again. And your cell phone, your laptop on your computer, they all use a secondary cell or a rechargeable cell, and you can recharge these cells, hundreds, thousands of times. Over time, though, we're not efficient in getting all the electrons back, and over time it kind of breaks down, and then eventually even a rechargeable cell won't recharge. And you maybe know that with your cell phone, sometimes you have to actually replace the battery. It gets really bad. So those are all dry cells, okay? And we tend to use a number of different elements to make these cells. You might have heard of lithium ion technology. Right now, that's sort of the reigning technology that works best for these dry cells. And one of my favorite companies, Tesla, uses them in their vehicles. There's some awesome advances in dry cell technology, though, that are just changing everything. Anyway, so that's a dry cell. Now, a wet cell, actually, I should come back. A dry cell uses two different metals, and we call those metals electrodes, okay? One electrode might be, say, zinc, and the other one might, say, be copper or something like that, okay? Or nickel cadmium is a classic one. I already mentioned lithium ions. But you'll note that if you break down any dry cell, it will have different metals, because different metals want electrons to a different degree. And so, a metal that really wants to get rid of its electrons, you'd make that the negative electrode, and then a material that really wants electrons, would be a good positive electrode. Okay, so that's simplifying it a little bit, but in general, that's a dry cell. Now, a wet cell, we're going to do some more with this shortly. A wet cell uses a liquid electrolyte, okay? So all of our car batteries, if you know anything about car batteries, they have a liquid electrolyte. It's typically an acid. We call it a battery acid. And that electrolyte's necessary for all of the wafers, all of the different divisions that are in your car battery for that chemical reaction to happen so that electricity will flow from the negative terminal to the positive. Okay? So again, but either one, wet or dry, they're called electrochemical cells. And the term that you should be able to separate, though, is if you have multiple cells together, they are known as a battery. Okay? So sometimes we say battery when really it's a cell. That's a common mistake. In drawing a cell, a typical cell is drawn as a short vertical line and then a long vertical line in a circuit. And so in a typical circuit, like we could have a circuit and we usually do that just as a simple line. It could be a bunch of things on that circuit, but that is the representation of a single cell. If we had multiple cells, then we would sketch them something like this, and lo and behold, you would have a battery. Okay, so to finish off, there's a couple of applications of electricity that we can use connected with chemistry. And yes, we call that electrochemistry. That's number 10. But you should know these terms. Number 9 is electrolysis. It's a process where we use electricity to separate individual elements from a molecule. And I'm going to attempt to show you this here. Let me see if I can pull this up. So if you can see on my screen here, this is electrolysis. And I'm just going to run the animation here. So the negative terminal is called the cathode, and the positive terminal is called the anode. Okay. And what's basically going to happen here, this is pure water, and we're going to energize the cathode and make it the negative terminal, the anode the positive. So at the negative terminal, we have basically electrons are at the negative terminal, and they react with the positive hydrogen ions. If you can see this, water is really H2O. So you can see there's two, there's red spheres with two white spheres on each one. The red spheres are oxygen and the white spheres are hydrogen. And so here what we have is we have the electrons that are at the cathode are combining or are joining up with hydrogen ions, and they make hydrogen gas. And so that hydrogen gas just bubbles out. And then here you can see the animation swings over to the anode. And at the anode, we have basically we have water molecules, we have oxygen molecules that are giving up their electrons basically, and they are forming oxygen. So what's really clever with of this process of electrolysis is at the positive terminal, so you can see this happening here, the positive terminal, we have oxygen that's forming as a gas and it's bubbling right out of the solution. And then at the negative terminal, the cathode, you have hydrogen gas bubbling out. And so we basically stripped, or we didn't strip, but we took the electrons and combined them with hydrogen ions to make hydrogen gas at the cathode. So electrolysis is really useful. That's about the most simplest one we could use there. Now, the other term you need to know is electroplating. Okay, so I'm going to see if I can pull this one up as well. And okay, yeah, actually, I think it's going to run here. So in electroplating, what we do is we coat an inexpensive metal with an expensive one, okay? And it shows this process happening right here where we have gold on the left here, and like an inexpensive metal on the right. And so we hook those up to a power source. You can see the two cells there. So we hook it up to a battery. And what's happening here is the electrons will go to the inexpensive metal, and as they accumulate there, inside the solution are gold ions. Okay, gold would be positive, and those gold ions will be attracted to the negative electrons. And you can see this reaction here, which you don't need to know, but gold 3 plus, Au is the symbol for gold. That'll combine with 3 electrons on the cathode, and they'll make gold. And so gold will start to layer on the negative ion. So if gold ions move out of the solution, then they must be replaced. And so over on the gold anode, it releases gold ions into the solution. And when it does that, it leaves behind 3 electrons. So those 3 electrons will actually flow back through the circuit into the positive terminal. You can see that happening up there in red. And that process can just keep happening. So electrolysis is actually the process through which we can coat an inexpensive metal. So I did show that a little bit here in terms of this sketch here. So this would be the cathode, and then this is the anode. Okay, and I didn't show all the steps on the inside, but it is a way to coat metals. We use electricity to do that. Now, we can also flip it around, and that is we can, instead of making it happen at the cathode, we can make it happen at the anode, and that is called anodizing. Okay, so you can see the root word anode is in the word anodizing. Okay, we do that with aluminum. In fact, if you guys are familiar with chain link fences, they kind of have a shiny coat to them, which enables them to not rust or to resist rusting for really long periods of time. And that is done with anodizing. Okay, and then the last term is electrorefining. We can also use electricity to separate impurities in a metal from the actual metal. So you can purify gold, silver, all kinds of things using electricity. So anyway, in short, you need to know all of these terms, and so I'd encourage you to study these. I know I went through them kind of quick. And shortly coming up, we'll do some work with wet cells, and then there'll be a bit of a quiz coming later. So anyway, keep up the good work.